All right, so without further ado, let's jump in. I think probably many folks here are aware of some basics about Julia, and if you weren't and you were here yesterday, then you now are, but I'll go through just one slide on some very high-level stuff about the Julia language. So it was established by a team out of MIT in 2012, hit version 1.0 in 2018, so relatively young language by scientific computing standards, but has been really, I think, growing tremendously in popularity and user base and all of these things. One of the big pitches is it was designed to solve the so-called two-language problem, where you would typically, maybe prototype some code in a very user-friendly, nice scripting language like Python, but then to get the really fast performance that you'd want for sort of a large-scale or HPC type of application, then need to sort of port that over to Fortran or C. Julia is generally the syntax is quite friendly and easy to write and learn and read. But there is kind of a pathway to sort of an iterative process of getting that real speed and optimization rather than needing to entirely re-implement or port your code over to another language. So that's been a big selling point. One really cool thing that we'll hear plenty about today, and that I'm certainly very excited about, is that Julia has, in principle, language-wide and quite performant automatic differentiation. So any pure Julia code should be differentiable by some way or another. There's also a lot of really extensive introspection tools through the metaprogramming tool set, which can aid in things like code profiling, benchmarking, and optimization, like I mentioned before, making that process a lot more smooth, as well as just like there's cool little macros and fun things you can do that I just find makes the language sort of fun and pleasant to use, which is something to be said for that. There's increasingly really great hardware portability across different things like different GPU architectures, which of course is more and more important for high performance in the modern computing landscape. Really good interoperability with other languages, so it's quite straightforward in general to call C, Python, R, etc. from Julia, and also usually to go the other way. I have not done the latter all that much, so but I've heard that is usually not too painful to do something like calling Julia from Python, etc. And I know there's some work going on to make that even easier to be able to sort of bundle binaries of particular codes and things like that. There's a really great, active, super collaborative online community. The Julia Molsim group is a largely online group. This is actually the first event that is just exclusively for that group that's not sort of a sub-part of some larger conference. So I'm very excited to make it not just an online group, but kind of bring people together in person. But it's definitely been something that I've taken advantage of a lot as I've been learning Julia and using Julia more. I can't tell you the number of times that I've had some issue and posted on the discourse or on Slack, and someone who developed the package that I'm having trouble with answers my question, or maybe even one of the developers of the language, so it's people are really invested in it and generally quite friendly and willing to help out, which is really wonderful. The core paradigm, as we explored extensively yesterday, and you'll get to see plenty of more examples of today, is the idea of multiple dispatch, and stated very succinctly, it's this idea that objects don't have methods, but rather functions have methods. So a function can have the same name and it'll have many different call signatures, and the Julia will determine which of those signatures, or which of those methods of the function to invoke based on the signature with which you call the function. And this contributes to a lot of the great sort of extensibility and code sharing and interoperability that has marked the beginning of the use of the language, which is really exciting. To paraphrase something that I first heard from Michael Herbst, who we'll hear from later, and he was paraphrasing Alan Edelman, who's one of the original developers of language. People compose when software composes, and I really like this idea that when you build a language that's easy for everyone, from the sort of hardcore applied mathematicians all the way through to the people who just want to run their simulation and see what the answers are, to all be able to use the same kind of language, the same syntax. It helps them collaborate with each other. It helps them develop new abilities, new capabilities, new tools. And I think this is really at the core of some of the really awesome collaborative ecosystem that we have, both within molecular and material simulation in Julia, but also just broadly in the Julia community, perhaps particularly in scientific computing, but I don't think exclusively to that at all. So then just a little bit about Julia Molsim as an organization. There's a few places you can find us online across the bottom here. So we have a GitHub organization, an associated website, and then if you want to chat with us, we have a Zulip server as well, and those are all linked from the website. If you Google Julia Molsim, all of these things are pretty easy to find. So it was started by Christoph back in 2019, I believe originally as mainly a host for kind of a private registry for packages to be able to sort of quickly, release new versions without all of the same restrictions that the big Julia general registry has. I think ended up becoming kind of a hub for collaboration. It's the host on GitHub of the DFTK and Mali simulation packages that you'll hear about in great depth later today. It has been the convener in real life, as I mentioned, of a variety of gatherings, including a few JuliaCon, Birds of a Feather sessions and workshops, mini symposia at the Pathways for Advanced Scientific Computing conference the past several summers, and also this workshop. Its discussions at these various events have really directly led to the development of some of the interface packages that you'll hear about in the next hour or so, including AtomsBase and Atoms calculators. So let's see if we can keep up that trend this week. Maybe some cool new collaboration will come out of some of the conversations and collaborations that we have this week. That would be really lovely. And so yeah, without further ado, that's kind of the background and the history. And I'll jump into a little bit about this interface we call AtomsBase. It was really, honestly, directly inspired, I think most directly inspired by the atomic simulation environment, which is a great set of tools in Python. I started out my PhD not knowing about this, and when I found out about it, it really kind of blew my mind how much easier it made so many things. And so definitely when I started doing some of this stuff in Julia, having a thought of, oh, it'd be really great to have a tool like that works really seamlessly with these tools as well. And if you're not familiar with ASE, you'll hear some more tomorrow, but I'll give you a very, very high level idea of it. So it provides this common atoms type for representing structures. So you can represent a structure, some geometry of atoms in some kind of box. Then simulation packages are interfaced through these associated calculator types that provide a common syntax across different codes. So you could, for example, run molecular dynamics with a few different MD engines by, in principle, just plugging in a different calculator onto the same structure. Hopefully it takes also the same syntax for various settings and everything, so you can do things like compare the performance or the results across different types of calculations. As I said, it allows a relatively straightforward combination and sort of mix and match usage of different types of codes in a workflow. One downside is that if you want to support a new package and you want it to work in really sort of a high performance way, it can take a pretty non-trivial amount of development effort to get all of those things to talk to each other sort of as efficiently as you would want them to make those handoffs really, really smooth. And so this is one place where Julia can come in and at least in principle, make some things smoother. I try to be careful when I talk about this stuff, occasionally it comes almost for free out of the box, but a lot of times these performance things in Julia do take work to optimize and improve. But I think many times in Julia, it is kind of a smoother path towards that. And that's a core point that I want to make. So the Julian way to achieve this similar kind of thing is the idea of an interface, which if you were here yesterday, you heard a little bit about this idea. But I'll introduce it again here. So the idea of an interface in Julia is it's not enforced in any formalized way. It's kind of an informal contract. Basically, if you dispatch all of these functions on your type, I will magically allow you to compute a bunch of other things. So one of my favorite examples of this, there's several built into the language in Julia. Some that almost everyone will come across are those for indexing and iteration of various kinds of collections of objects. So you can define a type, and if you dispatch a certain number of functions on it, then you can treat it almost exactly the same way that you would a simple array. Do things like iterate over it, sort it, and any kinds of things that you would do with lists of objects. One example that I really like is graphs.jl. So this is graphs in the sense of the mathematical object with nodes and edges. There's an interface consisting of just 10 functions. Likely, if you're loosely familiar with the idea of graphs, you can probably guess correctly what basically all of these functions do. Edges just gives you a list of the edges. Has edge, you just give it 2 node vertices, and it tells you is there an edge between those nodes. Has vertex, similarly. For directed graphs, there's is directed, in neighbors, out neighbors for a given node, list of vertices, number of edges, number of vertices of the whole graph, etc. So if you dispatch just these 10 functions on your new graph type, you can do a whole bunch of the fun things that mathematicians who like to think about graphs like to think about doing. You can compute various measures of centrality. You can do graph traversal algorithms, find the shortest path, detect cycles, graph coloring problems, all of these fun things that you might have seen if you think about these interesting kinds of problems. all of these things will work on your new graph type if you just dispatch these 10 functions. So that's the idea of an interface. AtomsBase is an interface for specifying atomic structures. So why might you want this? This is a little bit of a cartoon example, but I think it gets the point across. There's oftentimes different ways that we want to internally represent an atomic structure for the purposes of our own particular simulation. So very likely you would not want to do this for any kind of high performance type of system, but conceptually one could imagine an array of structs type of layout where each atom or particle is its own struct that contains fields representing, for example, the elemental symbol, position, velocity, mass, and then those all live in some box. Similarly, you could represent the exact same system via a struct of arrays where you just have arrays of all of the symbols, all of the positions, sort of indexing in index order. Now, if you wanted to, you could, these of course can store exactly the same information, but the syntax you would use to directly access that information would of course look a little bit different between these two. One thing I haven't mentioned here, but that will come up a little bit later, is you could also have different ways of representing that information itself, right? Sometimes we like to store relative coordinates relative to some particular coordinate system that specifies our unit cell, for example. Sometimes it might be more useful to store those coordinates in an absolute way on some sort of just XYZ Cartesian axes, irrespective of any particular symmetries of our system. And so all of these things means that there's certain transformations you have to keep track of, certain ways of indexing into things. And the idea of AtomsBase is to sort of abstract that stuff away and give you a unified way to access that information, irrespective of exactly how it's stored inside of an object. And that ends up giving us a nice common syntax that can be used for things like visualizing our system, doing file I/O, maybe featureizing for some sort of machine learning application, and just generally interoperability between different things. And I'll give a concrete example of that in just a moment. So currently, AtomsBase is a dependency of at least 27 registered packages. I'm careful when I say this. I initially had this slide as is implemented by, and I realize that's not quite true because not all of these define a system type that implements this interface, but somehow these depend on it. They show up in their project.toml file, for those of you who are familiar with Julia environment management. And these packages go across a wide variety of types of functionalities. So there's simulation itself, several of which we'll hear about later today. Simulation-related utilities for things like neighbor lists, interfacing with other sorts of tools for computing potentials, et cetera. Tools for structure building and visualization. By the way, many of the tools I'm listed here are developed by folks in this room or perhaps on the call. Circuitization for machine learning approaches, and file I/O, as I mentioned before. So this is just a taste. This has actually been, it's been a little while since I updated this. It's possible this number 27 has gone up a little bit, but this is a relatively, this project has been around for a couple of years. It's still a relatively small team of us who are working on it, but it's starting to get some traction. I think there's good, starting to be some good adoption and interest in this set of tools. And so one example of this kind of interoperability that this thing enables, this is maybe a year and a half ago or so, I gave myself the challenge of, can I implement an ab initio MD simulator, and in how compact a way can I do it using the tools from AtomsBase? And I'll preface this by saying this is absolutely not going to be fast or performant in any way. The point was just, this lets you prototype something like this really, really fast, which I think is very cool. So this is it. That's the whole code. The top, we just have some package imports and then a small converter to convert between fractional coordinates. I can go into detail into why I needed that in this case if you're interested. But let's just chop that off so that hopefully maybe some people can actually read some of the code. We'll zoom in a little bit here. And so basically to break this down, we have at the top here just some, one thing I didn't explicitly mention, this is AMD where DFTK, which you'll hear about right after 2 talks from now, is calculating the forces, and Molly, which you'll hear about later this afternoon, is doing the dynamics. So literally smashing these 2 things together. So the top here is telling us how to get the forces from DFTK and hand them off to Molly. Then we have some basic setup for the DFT, picking a pseudopotential, picking some smearing, all of these things that you know about if you do DFT. Some basic setup for the MD piece, and then running and visualizing the simulation. So that's the whole thing right there. Here's a little animation of my tiny, crappy AIMD simulation. It's like, whatever, 30 atoms or something. It ran in a few minutes on my laptop. I do not at all stand by the quantitative accuracy of the dynamics. The point is just that this was able to be prototyped in a relatively short period of time. Okay, so that's an example that hopefully motivates why this is a cool thing to have, in addition to some of the things I mentioned before. So what is this interface? And one thing I'll note here is that we released v0.4 relatively recently that has a couple of breaking changes in it, and some of the packages you'll hear about today still depend on 0.3. So some of these things, there might be a little bit of non-uniformity. But basically, there's this abstract system. So we have an abstract type to represent some kind of particle geometry. There's a core interface that basically says you should be able to index and get some information about the size, and then position particle masses and atomic species, some system level properties, the cell, the bounding box, and information about the periodicity of your system. If you have a mutable type, which not all types are mutable, you can optionally implement the setter interface to set these pieces of information. And then there's another optional component for extended properties for other types of things that you might want, perhaps related to magnetism or storing momenta are not sort of explicitly part of the core interface right now, as a couple of examples. And then we also provide some prototype implementations just to sort of demonstrate this idea. We do have one array of structs and one struct of arrays. One, to sort of plant a seed, one thing that's been coming up in some of the conversations on Zulip and GitHub recently that we might be able to talk about in more depth during some of the conversations tomorrow is our vision that these prototype implementations that we provide would be a thing that people would default to using, and that we would prefer that versus them defining their own types and then just dispatching the interface, or are we indifferent to those two things? I think there's some interesting conversations to potentially have there, and I think part of the goal of this workshop was also to bring in some perspectives from folks who had developed similar tools in other languages for other ecosystems and get other types of perspectives on pros and cons of those potential things. So I want to show some of this in a kind of a concrete way, and as it turns out, so there's more than one way that one can make use of this interface in a package, and as it turns out, actually the three packages we're going to hear about today kind of form an interesting set of principal axes in demonstrating this. So I have some stuff queued up here. Basically, I've pulled one example from the DFTK tutorial. Oh, that's not sharing the right screen. Okay, hold on. Let's close that down and go over to this. Okay, that's now showing up. Let's make that bigger and make that a little bigger. Okay. My goal is not for people to read every single line of this, but can folks see what's going on in the REPL here, like in the back of the room? Okay, all right, great. So an environment with DFTK and Molly in it takes a while, so I pre-compiled all of this ahead of time. But basically, I pulled I think it's the first example from the DFTK tutorial, where we build up a simple silicon lattice and make a system. So what DFTK does at the moment is it provides actually a converter to one of the prototype implementations. So I've built this DFTK system here, and it's actually it's the flexible system type, which is the array of structs prototype implementation. And then just for fun, I wanted to go the farthest length scale away, and Molly has a fun example where you're simulating the solar system. So I went the way other end. And built a little solar system in Molly. So you see these are order, 10 to the 30, 10 to the 24 kilogram mass particles. We build up the system. This is just in a cubic box of 1 billion kilometers on each side. We've got a gravitational interaction between them. And then we build up the system in Molly by contrast. Let me show this actually. The DFTK type here, this model, that's actually a DFTK internal type called model. And then this function here just converts it to that flexible system type. Molly, on the other hand, the Molly system directly subtypes abstract system from DFTK. And so we can actually, so it's a system type, but it is a subtype of abstract system. We can verify that here. Nope, can't. Why is that? Oh, because, there we go. It's a three-dimensional abstract system. So we can compare how we can get these pieces of information out. If I call position on that DFTK system, I can get out all of my positions in Hartree units here. If I wanted to directly access those, I can also do model.position. And one thing I'll note here is that internally here, it's storing it in relative coordinates. But then when we pull this out, it gives us the absolute coordinates. We made this decision in AtomsBase that we were going to ask for unitful absolute coordinates so that there'd be no ambiguity when you're kind of passing things back and forth in this way. Similarly, we can do this for the Mali system here. So these are much larger numbers, obviously. We can access them internally, and in this case, they look basically the same because Mali here is storing the absolute coordinates directly. There's a bunch of other properties that you could get if you want. So there's a bunch of other things being stored inside of this, not all of which does AtomsBase have interface functions for accessing. Our bounding box methods work. We can get the size of the box, big box. We can index into these both. The indexing interface works, just kind of showing that. We'll get out, in this case, we get an atom type, one of the AtomsBase atom types, and then Mali gives us what's this called atom view of a Mali atom. Building on the demonstration I gave yesterday, we can of course do cute little broadcasting things. So both of these systems are periodic in all 3 dimensions. And in this case, the DFTK system is immutable and the Mali system is mutable. So that's just a very, very short demonstration of this thing actually being applied to some of the specific things that you'll get to play with hands-on today. And hopefully you've seen some of the nice kinds of functionality that it gives us. This is just a short summary here. So we kind of, and I didn't directly demonstrate anything with ace potentials, which you'll also hear about, but so DFTK, as I mentioned, stores relative coordinates, and then right now it provides a converter to get out one of the AtomsBase types. I actually filed an issue last week when I was putting together this stuff, because I said, hey, it doesn't really seem like there's any reason you couldn't just directly subtype abstract system within DFTK. So that I might work on a pull request for that on the hackathon on Wednesday, we'll see. Mali's system type does directly subtype it, so you don't need any sort of converters, like I mentioned. Oops. And then ace potentials, which we'll also hear about, is completely agnostic, will take any subtype of abstract system and then ends up wrapping that basically inside of its own data types for sort of further annotation for computing some of these ML potentials. So that actually, timing-wise, worked out great. And I want to once more thank some folks. So the whole Julia Molsim crew, particularly those of you who are presenting this week, including Michael, Christoph, Timu, Joe. Chuck is not here, I apologize. Thank you, Chuck, as well. Ethan and Leticia, who ran a really wonderful intro to Julia yesterday. Everyone else who's presenting this week, I'm really excited to hear from all of you, and especially for bringing in some of these more external voices tomorrow. Again, to the MolC for financially supporting this workshop, and again, to all of you for being here. So thanks a lot. We have a couple of minutes if anyone has any questions about AtomsBase or any sort of logistic anything for the workshop, that's A-okay. And then maybe I'll let Timu come up and start getting set up while we have any discussion or questions. Thanks a lot.